Good evening, all. Welcome to live session 2 of Fundamentals of Convective Heat Transfer. Myself, Durga Prasad. I'm the teaching assistant for this course. I'm a PMRF scholar from Mechanical Engineering, IIT Madras. And my research area lies in applications of safety for understanding thermal and fluid dynamics of flows inside the building and glazing systems. And I'll be TA for this course for this particular semester. The sessions will be happening every Saturday from 5 to 7. This is the second session. We'll be having around 13 sessions this semester. The meeting link will be circulated to all the enrolled students on their registered email ID. And all these live sessions will be recorded and uploaded on YouTube. The link for the uploaded videos as well as all the slides that I will be discussing in the session will also be uploaded on a Google Drive. And the folder, you can access them from the course website. You can find the problem solving recording session, which will direct you to a Google Sheet where you can find the link of recorded YouTube videos as well as the material that is being discussed in this particular sessions. If you have any queries regarding the sessions, you can reach out to me on my email ID, mu22d400@sml.itm.ac.in. If you have questions, anything other than that is discussed in the session, if you have any questions regarding the assignment questions, or if you have any questions regarding the exam type or anything of that sort, you can raise those questions in the discussion forum. You can find that in the Q&A in the course portal itself, and they will be addressed by the NPTEL team. Just as a kind of a warm-up problem for whatever we discussed in the last week, you can quickly solve this problem, and then we'll get started with this week sessions. So this problem can assume the potato to be some kind of a sphere, which is not mentioned in the problem, but let's say the diameter is d, which is given in the problem. You're supposed to be cooling, you're trying to cool this potato by keeping it in a refrigerator. The velocity of air in the refrigerator and the temperature are given to us, and we need to estimate the initial rate of heat transfer from a potato, as well as the initial value of temperature gradient in the potato at the surface. So what would be the temperature gradient at the surface and what is the net heat transfer? I'll give you a couple of minutes so you can attempt and then we'll discuss. If you have any questions or anything, you can unmute yourself or you can also type in the chat box, whichever is convenient to you. So for the first part of the question, where we are asked to find the initial rate of heat transfer, so Q is given by, from Newton's law of cooling, we know it will be H times the total surface area of contact between the fluid as well as the particular solid surface times the T is the temperature of the surface minus T infinity, where or Tf is the fluid temperature. Here we are saying that the potato is cooled by refrigerated air at 5 Celsius and a velocity of 1 meter per second. So this will be, Tf will be 5 Celsius and potato is initially at 20 Celsius. So T will be 20 Celsius. And since it is a sphere, the total surface area of contact between the fluid and the solid will be 4 pi r square, where r is given to be 10 centimeter diameter, so r is 5 centimeter. And heat transfer coefficient value can be directly taken from this tabulated value, like velocity is given as 1 meter per second. So this is 19.1 watt per meter square Kelvin. Once we substitute that, we can calculate the value of Q. Did anyone get a value of that? Sorry, 8 point. 8.9 watts. So now let's before going to the second part of the question, let's say if the velocity is given to be a different value, let's say 0.8 meter per second. How would you go about solving this? Yeah. So what kind of interpolation would you be doing between 0.66 and 1? Linear interpolation or any other kind of interpolation? How would you decide the type of interpolation to use? Sorry, can you be a bit louder? Okay, okay, sure. So from what we understand in this particular week, we will be discussing on the scaling relations, where we will find that Nusselt number is proportional to Re to the power m. It is always of the form of some power. All the heat transfer correlations that we'll be encountering in this course, that you will find again, this keeps coming up again and again, that these actually follow power laws. So the heat transfer coefficient will also follow something of the kind C1 times velocity to the power n. It's like it would follow a power law. So whenever we have a power law, so linear interpolation might not be the accurate way of doing interpolation. So what we have to do is we can apply a log transformation. So once we apply the log transformation within the log variables, like the ln of heat transfer coefficient and ln of velocity, these values would be, this equation is linear in nature. So then we can apply the linear interpolations. Essentially what we have to do is we have to create a table from this, where we will have ln v and ln h. So corresponding 4 values will be here. Then we have a new value at 0.8 meter per second that we are trying to interpolate, which we can interpolate between these two. And then that would give us the heat transfer coefficient at any intermediate velocity, let's say 0.8 meter per second or any other velocity we wanted to do. I hope that is clear. But anyway, that is not part of this question. I hope that is clear. Let's move on to the second part of the question, where we are asked to find the initial value of the temperature gradient in the potato at the surface. How do we calculate the second one? And there are two other things. Again, we are asking initial rate and initial value. We'll get back to why is this the initial value and why will it change with respect to time. That also we'll discuss. But for now, let's say, how do we calculate the temperature gradient in the potato at the surface? This we have discussed last week, that at any solid interface that we have between a wall and a fluid, we need to satisfy two conditions. One, at the interface, if this is the interface, both from the solid as well as the fluid side, the temperature has to be continuous. So at the interface, they'll have the same temperature. Temperature has to be same. And second, the heat flux should also be the same. So within the potato or within the solid surface, the heat flux is given by minus K times del T del N. I'm just writing N so that it is normal to the surface, times the corresponding area. So in the potato surface, when we have a spherical surface, so that just the interface will be having like a spherical shell. So this heat flux would be given by K times the total surface area times the temperature gradient. So I'll just write it as grad T for now. This should be equal to the net heat flux that you have obtained from the previous case. So I'll just put a minus here. So we know the thermal conductivity is given as 0.049 watt per meter Kelvin. The radius is also known to us, and we are asked to find the temperature gradient. So you can Q is we have the value is around 8.99 watt. So you can substitute that back, and then that will give you the value of grad T dot n cap. This is the temperature gradient we'll get. I think this is straightforward math. So I will just give you a minute so you can solve and let me know the answer. And the other interesting point here is the question clearly asks you the initial rate and initial value. Why is this? So if you recollect, conduction is not actually part of this course, but a kind of a prerequisite one, where we also discuss something called lumped parameter models, where we discuss a number, non-dimensional number called Biot number, which is basically heat transfer coefficient times the characteristic length divided by the thermal conductivity of the solid. And if this particular number is less than 0.1 or so, then that particular solid can be considered as a lump model, and all the temperature gradients can actually be or close to zero inside the solid. But for this particular problem, you can calculate this value and let me know what the value of Biot number is, and where the this characteristic length is given by the total volume of the solid divided by the total surface area, which in this case runs out to be radius by 3. You can compute this value and check if it is less than or greater than 0.01 or 0.1. 0.65, so which is greater than 0.1. So the usual case set of lump model cannot be used here. So this is what we would have studied in the heat conduction part, where if this Biot number is greater than 0.1, then temperature gradients are significant, and you have to consider that in your modeling aspect. So which means this, that is why the question is explicitly asks you to find the initial value of the temperature gradient, which as the time progresses might be changing. Okay, are there any questions? Are there any doubts? I think this question is clear. What was the value for the temperature gradient that you calculated? Around minus 580 or something, Kelvin per meter or Celsius per meter. In this case, it doesn't matter, both are the same. So you can see the amount of temperature gradient that we'll be getting just at the surface of the potato. And this gradient will keep reducing as a function of time. So this is just a recap of what we discussed in the last week, where we discussed about the Newton's law of cooling, and from there how to determine the surface temperature. Like as I said, there will only be two kinds of problems in this particular course. You will either be given the surface temperature and asked to find the heat transfer rate, or the other way around. You will be given the heat transfer rate and you will be asked to find the surface temperature. And in this particular problem, heat transfer coefficient is given in a tabulated form. But as the course progresses, we will see that in this particular case, heat transfer coefficient is only a function of velocity. But then we'll also see that it is a function of other flow properties. And then now in this particular week, we will introduce some non-dimensional numbers like the Reynolds number. And then next week, we'll actually get this heat transfer coefficient as a function of Reynolds number. And then we will use that to estimate all these values. Okay. So this week, particular in the lecture videos, I hope you have already gone through the lecture videos. Do you have any specific questions in the lecture videos that you want me to address? So the first module of this week discusses on Reynolds transport theorem, which essentially helps you to relate conservation of a property in the Lagrangian versus Eulerian approach. So in general, if n let n be any extensive property, which means it increases proportionally with the mass of with the mass. So then we'll have the rate of change of n with respect to time between the system, where system is the collection of particles that you have, is related with the control volume approach, where you have the partial derivative with respect to time of that same quantity, where eta is the intensive variant of the extensive property. So n will be given by rho times eta. So this is like the total change with respect to system is given by the total change in the control volume. So this is what is happening inside the control volume, and we also have to track what is going in and out of the control volume. That is given by the surface integral. So this is Reynolds transport theorem, and again, as I said, as a prerequisite of this course is a fluid mechanics, where you would have tried different quantities. For example, when eta equal to 1, you get mass conservation. When eta is velocity, you get momentum conservation. And in this week lecture videos, you would have seen specific energy as eta is specific energy. Then you will get the energy conservation equation. I'm not going to go through the derivation again because it has already been discussed in detail in the lecture videos. It's the final equation that is of interest to us for the problems that will be there. So I'll be just writing the final equation where we have d by dt is the material derivative with respect to temperature. So rho Cp dt by dt is the total energy can be written as rho Cp. This again is the total material derivative, which can be written in terms of, again, this I'm writing for whenever I write this particular term, we are like I have taken rho Cp outside. As I said, this entire course is on incompressible flows, and as we discussed last week, we are assuming density to be constant. But when I mean incompressible flow, what essentially it refers to is that the flow has Mach numbers less than 0.3, which essentially boils down to the case that rho is not a function of pressure. So rho can be taken out of all these ones, and we'll be having this equation given by, this is the total derivative of the internal energy change, which is given by the conduction, the heat generation within the control volume, and then we have heat transfer due to conduction, which is del dot thermal conductivity times del T, and then we have one more term, which is again something which we will be neglecting for most of the time in this particular course, except for a couple of weeks. This is the viscous dissipation term. So this additional term is coming because of whenever there is a velocity gradients, there is a shear stress coming up there, because of which, because of that friction, there will be some of the energy that will be converted into heat. And this heat should also be added as a source term to our energy equation. And this becomes important especially when you have this phi is something that will depend on velocity gradients. Say for a 2D flow, phi will actually come up to be something of this kind, where this viscous dissipation term is, again, all these terms are velocity gradients. So wherever we have velocity gradients either in the x or the y direction, then this term will be adding. But for most of the cases that we will be encountering in this course, these terms are actually very small and they can be neglected when compared to other terms. Just to illustrate that, I had one more problem. This is again to show that when this term is significant or not. So consider a flow. Fluid is flowing steadily between two infinite parallel plates. So you have two parallel plates which are extending in infinite direction in both ways. And that is, let's say the origin is at the midpoint and we have H, H. So this is plus H and this is minus H. This is my coordinate system. And if both the walls are at the same temperature, and the velocity profile between these two parallel plates is given by, again, this you would have already come across in fluid mechanics, where if you have two parallel plate channel flow, then the velocity flow would be a parabolic in nature. Say something, we have a velocity profile of this kind. The energy equation is given by this equation, where again we are assuming that temperature variation along the x direction is negligible, and then this is a final equation we would be getting. So this is where we started out with. So we are assuming steady flow, and then we are assuming the temperature variation along the x direction is negligible, so the LHS goes to 0. There is no heat generation within the solid, so that essentially means there are no heating elements in the fluid. In the parallel plate channel, whatever we have considered, if for example there is some solid object that is getting heated or some kind of chemical reaction is happening which is generating heat, then this term would be non-zero, which is not in our particular case, so this is equal to 0. Then we have the gradients term. Again, thermal conductivity is assumed to be constant, so we'll have K times del square T. Again, as I said, along the x direction we are neglecting the temperature variation, so this will be the term. And we have mu times phi. Since velocity in a parallel plate channel flow is only varying along the y direction and v is 0, du dx and del v del y will be 0. And out of these two terms, again v is 0, so this is the only term that will be left with. So we will have du del y whole square equal to 0. So this is how we get this equation. Now, can you solve for the temperature profile and find the maximum fluid temperature? So before even solving, where do you think the maximum temperature will occur? So there is a heating that is happening. So because of viscous dissipation, some amount of heat will be generated inside. So because of that heat, temperature will change inside the fluid. So where will the maximum temperature occur? At the center line. This is a symmetric channel. We have both the walls at the same temperature. So the maximum temperature, like whatever heat it is getting here, it will has to reach TW, it will has to reach TW. So the only place where the maximum temperature can occur is at the center line. Now let's say instead of both of them being at constant temperature, if one of them is insulated, let's say the bottom plate is insulated, then what would happen? Or that would be one scenario. In other cases, the top one is insulated. These are all different scenarios. Again, all of them we will discuss in once we actually get into, after we solve the boundary layer equation, and then we'll go into internal flows where we will discuss all these different scenarios also, which will be in the upcoming courses. For now, let's we know that this is going to be symmetric and the maximum temperature is going to happen at the center line. So how is this maximum temperature related with the wall temperature? It should be definitely greater than the wall temperature. So I'll just put at plus delta T, and our aim is to find this delta T. That is second part of the question. And the first part of the question asks you to find T as a function of Y. This is again a prerequisite. So the prerequisite of this course is for you to able to solve differential equations, which will not be discussed in detail in this particular course. So we have delta T will be between the maximum temperature inside the fluid, that is the center line, and TW is the wall temperature. So because Tmax is going to be higher than wall temperature, so I'm just writing it as TW plus delta T. This is the temperature rise that is happening because of this viscous effect. So with this, we can solve the first part. So u is given. So du dy will be given by, or maybe should I give you a couple of minutes so you can solve this? You can u is given to you, so you have to calculate du dy, substitute it in this equation, and solve this differential equation with the boundary condition that the value of temperature at minus h and h is Tw. Or you can also solve this in a different way, where this is one way to solve, or you can just take only half the domain. And as we already know that the maximum temperature is going to happen here, and wherever maximum temperature happens, the temperature there dt dy should be 0. So you can just take half the domain and solve the same differential equation with the boundary condition that at the top y equal to h, t equal to tw, and at y equal to 0, dt by dy equal to 0. You can solve either way. And wait for a few minutes so you can solve it. Hope you are also getting the same answer. Okay. So we have the velocity profile. First, you would calculate du dy. Then we would substitute that in this equation, and then we integrate it twice. So for the first integration, we have C1. We know the maximum occurs at the central, or because of symmetry, we can set dt dy at y equal to 0 should be 0. So C1 has to be 0. And again, we integrate it. Then we get t of y as this expression. And at y equal to 0, this should be equal to tw, and at at y equal to h, this should be tw, and y equal to 0, this should be t max. So t max should be equal to c2. So from which I know delta t is basically this value, whatever we are getting here at y equal to h. So I would get this expression for delta t. Now we can actually compare and see whether what happens if we have air. If you are using air, take thermal conductivity to be around 0.026 watt per meter Kelvin, and mu is say around 1.8 into 10 power minus 5 Pascal second. And then let's take usually for lower velocities around, let's say 10 meter per second or something. This itself is a very high velocity. Around 10 meter per second or so, what would be the value of delta t? Can you quickly calculate this and tell me? It's not visible. Is my screen visible now? Okay, I've missed the chart. My code is not visible clearly. Is it visible now? Do you still have the same problem? Can you confirm if it is visible? It is visible, right? Thank you. So you're saying delta t was around, so I got around 10 power. like the order is around 10 power minus 3 minus 2. So you can see the value of delta T is very low. So for usual cases, when we consider air at low velocities, this value is negligible. So usually we neglect this particular term in our energy equation. So from here forward, like most of the equations, when we say energy equation, we usually neglect this viscous dissipation term. However, we'll also see some problems where you have, say, engine oil or something which has very high viscosity. In those particular cases, this term will become significant, and without it, like the physical significance itself would be gone. So this becomes important in some scenarios, because you see the maximum temperature if happens somewhere away from the walls. So somewhere in the center or some other reason if that happens, and the whatever lubricant or whatever engine oil you're using, if the temperature there exceeds the boiling point or the flash point for that particular one, then it will just evaporate there. And that is not, and sometimes that can also cause deterioration of the materials that are there. If you have, say, ball bearing or something, and then this hot thing with like when you design for a particular temperature, but then the operating temperature is actually way higher than what you have designed for, then that could also lead to failures. So this term becomes important in under certain scenarios, but can be safely neglected whenever we're dealing with air. So to ascertain when this particular quantity is of interest and not, we have another non-dimensional number that we'll be using, just like Reynolds number and Grashof number that we discussed last week. We have one non-dimensional number that will tell you whether this particular term is significant or not, which we'll also discuss in the upcoming week. So where this particular one can actually be expressed in the non-dimensional form called Brinkman number, and that magnitude of that number can be calculated beforehand itself with a characteristic velocity scale and viscosity, thermal conductivity, and specific heat and other terms would also be coming into it. And that will tell you whether you have to include or safely neglect this particular term in the energy equation. I hope that is clear. Okay, that is with respect to the module 1 of this lecture this week. The second module starts with the scaling analysis for boundary layer. Because that is already discussed in the lecture videos, I would like to take up a slightly different problem from conduction, which also follows the same arguments, just to make sure that you understand what scaling analysis is. Even in boundary layer equations, whatever is discussed in this week, first we will start with a set of governing differential equation for that particular problem. So this equation is for a fin. A fin is essentially you have, let's say, a surface, a wall is there, and then you have some extended surface from the wall, something like this. Let's say the wall is at a temperature T naught and the fluid is also at the same temperature. This is an entire external surface of thermal conductivity K, and A is the area of cross section. So if I cut it at any particular point at a distance x, the area of cross section of this particular one is A, and the perimeter, which is basically the total length of all these sides, is P. This surface is getting cooled by an ambient air, and the heat transfer coefficient is given by H. And the ambient is also at the same temperature as the wall temperature T naught. Now let's say this is extending like this. And Q triple prime is the volumetric heat generation rate that is happening inside the fin. So something is happening within the fin that is generating heat, say kind of nuclear rod or something, where some reaction is happening and that is generating the heat within the fin itself. So this is the total differential equation that we are trying to solve for. Now, based on the scaling arguments that whatever is discussed for boundary layer equation, even if you see the boundary layer equation, you would have, it would be a second order differential equation of this kind. Like you will have d square u by dx square term, and then you will have u times du dx term. So it is of similar kind, just that this is only in variable x. In our boundary layer equation, we have both x and y, but this is only in terms of x. So this just to simplify things so that you can understand the scaling analysis better. So what would be my first step in scaling analysis? So there are three different terms and I want to understand the relative contributions of each of the terms. So this is the conduction term. I'll call this the conduction term. This is the convection term. And this is the generation term. So what would be the first step before doing the scaling analysis? So the first thing when we start with scaling analysis is we do some kind of non-dimensionalization so that we can estimate the order of magnitude of each of the terms in the differential equation. So in this particular case, we can write this as, or I'll just use a non-dimensionalization where theta is given, I have directly written the equation in terms of theta, where theta is given by t minus t naught. And then we also have x, let's say we non-dimensionalize it by capital X times some length. This is a length scale that we do not know yet, which we will try to figure out. So if I substitute that back into the differential equation, that would give me Ka by L square d square theta by dx square. Again, this is with respect to some reference temperature minus Hp times theta. So now we have to do the scaling analysis where we compare order of magnitude of each of the terms. So the first one will be of the order Ka by L square. This one will be the order H times P. So for the first part, to understand where conduction and convection are the only important terms. So only if we scale between these two terms, conduction and convection terms, then we would have, so when the characteristic length L or the X that we are considering is of this order, then these two terms will be significant. Or now if you want to compare the other two terms, for example, if you want to understand where this term is negligible compared to the other term, or let's say I will put it as if the conduction has to be neglected, something of this kind. So if you are considering a region which is very far away from the particular from this particular point, if L is very far away from the wall origin, then you can actually neglect the thermal conduction term. Because L is very high, this particular term will be negligible compared to the other two terms, and we can directly solve for theta from this. So then we will get theta as, or you can also consider the other way around where this term is actually significant and comparable to the convection term. So if I put it the other way, so when L is very much less than square root of Ka by Hp, then conduction term cannot be neglected. And these two terms become significant. Or the other component, you can also consider another length scale where Ka by L square is of same order as Q triple prime A. So that would give me L of the order. So we have three different length scales, each one deciding which two terms are important. So you, depending on where you are in the region, those terms will be important. Maybe if I give some numbers, then it will be more clear. Let's take some numbers. So let's say the differential equation is of like this: d square theta dx square minus let's put some number 4x plus 1 equal to 0. Let's say this is my differential equation, and my boundary conditions are at x equal to 0, I have theta equal to 0, and x equals to infinite, I have theta prime equal to 0. So this is my system of equations that I am trying to solve. What is the solution of this system? So before even solving, we can directly see what I was trying to explain before. So there are three terms that we are trying to understand which of the terms are important in when we are solving the differential equation. So if we say that we are very far away from the origin, when L is very large, this particular coefficient is very small, so this term can actually be neglected. So when for x tends to infinity, this particular term is actually small, and these are the only two terms that influence the final solution. So when x tends to infinity, we'll be having, sorry for the typo. So this is 4 times theta. So when x tends to infinity, this particular term will actually be negligible, and then we'll be having with theta equals to, theta will tend to 1 by 4. And similarly, what happens when I'm close to 0? The actual solution for this equation is something of the kind 1 by 4 times, which essentially is, if I plot this, it will be like at x equal to 0, this will be 0. And as I go towards infinity, so this will eventually approach 1 by 4. So what do we mean by when we are trying to balance this? Maybe I'll show you on a small plot. So the equation, we have three terms here. So we'll take one, like this is a final solution that we already know. Now what we are trying to do is we compare the contributions of each of the terms in the differential equation. So our first term is d square theta by dx square. If this is theta, what is d square theta dx square? If this is theta of x, what would be theta double prime? Theta prime is going to be e power minus 2x by 2, and theta double prime is going to be e power minus 2x times minus 1. So the magnitude of this is e to the power minus 2x. If I just plot that, so this is my, so you can see this is my first term in the equation, and let us see the second term. The first term is d square theta by dx square. The second term is 4 times theta, which is 1 minus e to the power minus 2x. So I'll just plot that one also, 1 minus e to the power minus 2x. So this is the second term, and then we have the third term, which is a constant, which is equals to 1. So now you can see the relative contributions here. When x tends to infinite, this first term, this is f of x, conduction term. This is the conduction term, and this is the convection term. And then y equals to 1 is basically my heat generation term. As you can see, when x tends to infinity, as we go very far apart, the conduction term is actually going to 0, which means in the differential equation, the first term that we are considering, the contribution of this term to the overall differential equation will eventually go to 0 as x tends to infinity. Similarly, when x is close to 0, the contribution from the convection term goes to 0. So the balance is happening between conduction as well as the source terms. So this is one region and this is the other region. These are the two extreme regions that we are considering. So similarly, what we have even in the fluid case, we have two distinct regions where in one of the region we have viscous effects being dominant. So that is the second order derivative versus the heat generation is essentially what we have like in our boundary layer equation. You see that there is certain region where this term dominates. That is our boundary layer region, and beyond a particular point, the second order derivative will become small enough so that the other terms will balance each other. That is, the inertia and the pressure forces will balance each other, where your Euler equation will apply. That is in the outer region. So in a boundary layer, you'll have two different regions. There will be an inner region where you'll have the second order derivative becoming important. So that is our boundary layer region. And then as we go far away from it, so this is where your Reynolds number, that is inertia versus your viscous effect. So that is inertia term is your, so if you write the boundary layer equation, so that you'll have u times del u del x plus v times del u del y minus dp dx times 1 by rho plus nu times del square u del y square. So if you compare this equation with this equation, so the theta is kind of u here. So we have a double derivative term here, and then this is my convection term. or in the case of our boundary layer equation, that is my advection term. And this is the source term, that is the pressure term, that is Q triple prime here. This is the pressure term that we are having. So what we are trying to understand now is what we observed, the same thing that you are seeing in this graph. So very far from it, we will see that the conduction term is actually negligible. So which in this particular case is this term. So very far from the wall, you have d square u del y square becoming 0. So this effect of this will become 0, and it is only inertia versus pressure. These are the only two important terms in the different in the momentum equation. And when we go close to the wall, it is the convection and conduction. These two play a major role. So which essentially means inertia is balancing my viscous forces, and the effect of pressure will actually reduce. So without actually solving the final equation, like here to illustrate, I have shown you that we actually need a solution here. And from that solution, I tried to show you that these are happening. So what people have done is when they perform the experiments, they evaluated all these values. They know they measured velocity at different locations. And from there, they evaluated each of these terms. And from which they identified that there are certain regions where some terms are important and certain other regions where they are not. And from there they are able to verify that the assumptions, that the scaling analysis, like you can also do the scaling analysis, from which they found out this in this region you have a certain region called delta within which these equations are valid, and these are the boundary layer equations that are discussed in your lecture videos. And how to solve those equations is again something that will be discussed in the next week. There are different ways that in the coming next 2 weeks we will discuss different ways to solve this set of equations, but the idea is to give you an intuition of what we are doing in the scaling analysis. Are there any questions? We are like halfway through the session. Are there any questions in this? I hope this is clear. Again, just to re-emphasize, when we have a difference, yeah, have some question. Okay. So just to reiterate again, when we have a differential equation which is complex enough to solve, so what we identify is we understand the relative contribution of the terms which changes from region to region. Then we can actually use a scaling analysis which says that in a certain region, some of the terms can be simplified, and then the equation will reduce to a form which can be solved in some simpler way than solving the overall equations. Like as you know, like when we start with Navier-Stokes equations, which is very difficult to solve. So then we understand that there is this scaling behavior where the relative strengths of each of the terms is different in different regions. So we will split the entire domain into different regions, and in particular regions we will simplify the terms accordingly, and then we will solve the solutions in each of these regions separately, and then we will see how to match them across these different regions. That is also something that we will do towards the end of the course when we start turbulent flows, where this concept comes again, where we understand the we use a similar idea, but then we'll act, for example, in order to solve this equation, what we did now is we actually solve this using whatever techniques that you have already learned, like you assume a particular solution and then a general solution, like you assume theta equals to c1 e to the power x plus c2 e to the power minus 2x, and c1 c2 as a function of x, and then you solve it, like the usual way that you solve differential equations. Instead, we can also use an alternate approach where we know that as at theta tends to infinity, as x tends to infinity, this contribution of this term is negligible. So we got theta equals to 1 by 4. Similarly, when x tends to 0, we will know that these two terms are comparable to each other. So we can actually solve this equation and get one solution. Now what we have to do is match this solution with the other solution in some intermediate region. So this is the total domain. So here we know that the first term and the third term are comparable with each other, and then there is a small region here where these two terms are comparable with each other. But everywhere in between, all the three terms are important. So which means we will have to anywhere solve the entire equations. So this is something that we'll encounter in turbulent flows also, where we use a different technique to solve this. I'm just kind of giving you a heads up so you know how to relate it when we discuss turbulent flows, that this is some problem that we discussed before, so we can relate with this later. I hope this is clear. Okay, this is some general questions to kind of refresh on whatever you have already seen in the lecture videos. Consider a steady laminar two-dimensional flow over isothermal plate. Does the thickness of velocity boundary layer increase or decrease with these three cases? So as you go from the leading edge, so this is my isothermal wall, the fluid and the wall are at the same temperature. So there is, if both are at the same temperature, then my thermal boundary layer thickness will be equals to, if wall temperature and fluid temperature are same, then the boundary layer the thermal boundary layer thickness will be equals to, this is like saying if I have a plate that is not fixed but is moving at the same velocity as the air, so that the relative velocity between the plate and the air is 0, then what would be my velocity boundary layer thickness? So the reason boundary layer is forming in the first place is because we have a velocity gradient. So when I have both the plate and, so if I have both the plate as well as the air, both are moving at the same velocity, then there is no relative velocity between them. Then it would essentially mean there wouldn't be any velocity gradient, so the boundary layer thickness should be equal to 0. The same case applies even for temperature case. If both the free stream as well as the plate have the same temperature, then the thermal boundary layer thickness will also be 0. So only when we have the difference here, then the information that, for example, the air that is flowing here has a certain velocity, which is different from the velocity that it is going to encounter at the wall. Whenever the fluid reaches wall, it's because of the no slip condition, the velocity there has to become 0. So the air particles here uh, need to know that there is a wall here. So that is where this boundary layer thickness comes. So any air that is moving above the boundary layer thickness will not even know the presence of this particular wall. So they would not experience any shear because of this wall, while the particles within the boundary layer will actually notice the presence of wall. That is why their velocity will get reduced. Since we have that velocity gradient. So now the question here is, this is the distance from the leading edge, x. So as I go farther away from the x, will the boundary layer thickness increase or decrease? So you can see here, I've already drawn it, so it is quite straightforward. But yeah, I shouldn't have drawn it in the first place. So here I have drawn that the boundary layer thickness is actually growing as a function of x. So as the distance from the leading edge increases, the velocity boundary layer increases. So even from the scaling analysis that we already discussed before, or in the lecture videos, you find that the relative contribution of the term. So if you take the boundary layer equation, the inertia term is u times del u del x versus the viscosity term, which is nu times del square u del y square. So we are trying to balance inertial forces with viscous forces. That is how we will determine the scaling for the particular delta. So in this, u will scale as u infinite. That is a free stream velocity. Del u del x will also be written as u infinity, by x is that particular distance from the leading edge. That would scale as mu times, again del square u del y square will be u infinity, by y will be the distance from here. So this is my y axis. So the distance up to this will be delta square. If I rearrange this a little bit, so I'll be getting u infinity times x by nu, be scaling as x by delta square, or I can write this as delta by x would scale as, this is my Reynolds number, u infinity x by nu to the power minus half, or I can write as delta is scaling as, from this I can write delta is scaling as square root of mu x by u infinity. This is again just an order of magnitude analysis. So which essentially means delta is scaling as this. Of course, delta will be equal to some constant times this value, and we do not know that constant yet, which is something that we will discuss next week. How to find that constant is something we'll find next week. But for now, the idea is to show you that delta is actually scaling as this. And how did we obtain this? Is by the balance between inertial as well as the viscous forces. This is only in the boundary region. Once we go away from the boundary region, again this term becomes negligible, and we have to do the balance between pressure term and this term, inertia and pressure term. There you will get a different number, which is again something that we are not discussing, but you can try it out as a self exercise later to see what happens when you do a balance between the pressure term and the inertia term, so that you will actually come up with Bernoulli's equation later. You can try that out as an exercise. So here we know that delta is proportional to nu x by u infinity. Now, once we know this scaling relation, we can answer all these questions. So as the distance from the leading edge increases, so which means x increases, then delta will also increase. The second question is with respect to the free stream velocity. As u infinity increases, delta, because they are inversely proportional, this will reduce. And kinematic viscosity is directly proportional to delta. So what this means is if I increase the velocity, in the free stream velocity, then the boundary layer thickness reduces. So what would that mean? Like, will my shear stress increase or decrease? I should have added it. Okay, let's take another part also. What happens to shear stress? Will it increase or decrease? No, shear stress at the wall. Sorry, your voice is not clear. So shear stress at the wall, you are asking something? I cannot actually hear you clearly. Maybe can, yes. Yeah, now I can hear you. Regarding shear stress, what I was asking is similar to this. What happens to the shear stress at the wall as you go away from the leading edge? Like this particular question asks about how boundary layer thickness will increase or decrease with respect to all these quantities. So in addition to boundary layer thickness, I would like to ask what happens to the shear stress at the wall, that is tau W, as a function of x. And then from there, we will relate this tau W with delta and see how is tau W related with delta. So we can use the Newton's law. So tau W will be mu times du del u del y. So which means tau W will actually scale as u infinity by delta. So tau W is inversely proportional to delta. So as the free stream velocity increases, what would happen? So this would be mu times infinity times square root of u infinity by mu x. So as the length of the plate increases, tau w will actually reduce, and as u infinity increases, your tau w will actually increase. So the intuition that I wanted you to remember here is the relation between tau w and delta, which is something that will come up again in the next problem. So if you want to, as the boundary layer becomes thinner and thinner, so if delta reduces, then the shear stress increases. So that is the point I wanted to take away from here. If the boundary layer becomes thinner, then shear stress increases. So as you go farther and farther away, your boundary layer becomes thicker and thicker. So your shear stress reduces. So now if we, I think this part is clear. Then we'll move on to the next problem. This is again another important part in this week session. So I hope you've already gone through the lecture video, but again, since this is important, I would like to uh, explain the same thing again. So how does so in the previous example, we have considered an isothermal plate where the wall temperature and the free stream temperature both are same. So we do not have any thermal boundary layer thickness. But in reality, what happens is the surface that you are encountering and the free stream will be at different temperatures. So there will be a heat transfer between them, either to or from the wall. So then we define Nusselt number as the heat transfer coefficient times one characteristic length by kappa is, again, this is thermal conductivity of the fluid. Okay, so one more point. So what is the characteristic length we will use for this flat plate is the length along the flow direction. So why aren't we using the length along the other direction? That is also something maybe we'll discuss a little later. But for now, let's say that this length is the length along the flow direction that we are considering. The characteristic length is along the flow direction. This is for external flows. When we move to internal flows, then again this characteristic length definition will change. So depending on the problem, this changes. How do you decide which characteristic length to use is again something that we will discuss a little while later. But for now, to determine the Nusselt number scaling with Prandtl and Rose number for different cases, again we come to the same point where we start with the balance between different terms. So we already know that u times del u del x between the inertia term and viscous term. When we do the balance between inertial and viscous forces, we came to the equation that delta by x is of the order of rex to the power minus half. This is what we got in the previous case, but we kind of assumed something which I did not state explicitly. Now let us make it more explicit. So this is that is for an isothermal wall. Now when I have different wall temperature and the free stream temperature, now I can have two different scenarios. I can have one case where, let's say this is my velocity boundary layer and this is my thermal boundary layer. So both the boundary layers can be of different sizes. And this is happening because, as I said before, this is about how the gradients propagate. This is how far the influence of this wall has reached into the free stream. For a velocity, it is about the viscous dissipation. For a thermal case, it will depend on the thermal diffusivity alpha, which depends on thermal conductivity. So we will see that as well. So if this is, you can have two scenarios. Case one is when you have delta greater than delta t. And then we can also have a different scenario where delta t greater than delta. So there are, depending on which case you are, the scaling analysis will actually differ accordingly. So for example, let's take the first case. So when delta is greater than delta t, when I'm doing the balance between inertia and viscous terms, for the first, this comes in the momentum equation. So I'll be considering the velocity boundary layer. Here temperature, this balance would actually give me this equation. And then we'll also do the same thing in the energy equation. So in the energy equation, we'll have, instead of velocity, we'll be having temperature. Del T del X should be in the order nu times del square T del Y square. And for case one, when delta is greater than delta T, So for the thermal boundary layer, I'm writing this equation within the thermal boundary layer. So this equation is valid only inside this region. So which means the velocity scale that I should be using should be the velocity at this point and not the velocity at the free stream. So I'll have to again do some kind of analysis, some kind of relation between the velocity here, which is the free stream velocity, versus the velocity that is going to happen at the end of thermal boundary layer. And again, we can use the similarity law, which says that the velocity here, when related with just like in similarity triangles, these are proportional to the distances from the wall. So which in this case will be, here it will be delta u is here and this is u infinite. So at u we'll be having delta t and at u infinity we'll be having delta. So the velocity u is in the energy equation will be related with the free stream velocity by this equation. So now if I substitute that back in the scaling analysis, so I'll have u infinity times delta t by delta, del t by del x, so there will be some delta t divided by del x is x, scaling as, sorry, in the energy equation we'll be having alpha, the thermal diffusivity, times delta t. Again, as I said, this equation is only valid in the thermal boundary layer. So I should be using the corresponding length scale for y, which is delta t. So now we can do a little arrangement here. So u infinity times delta t cube by delta by x should be scaling as alpha. And you already know that delta by x is scaling as mu by u infinity x to the power half. So I can get from this u infinity scaling as nu times x by delta square. So nu infinity by x is going to be nu by delta square. So I can substitute this back into this equation, which gives me delta t by delta cube scaling as alpha by nu. So this means delta t by delta, and this number is nu by alpha is Prandtl number. So delta t by delta is Pr to the power minus 1 by 3. And now coming back to the original, the way we are trying to establish Nusselt number scaling. So Nusselt number is given by, so in order to get Nusselt number, we need to first define the heat flux. The heat flux is given by the heat flux in this boundary layer region, again, is the thermal conductivity of the fluid into delta T across the boundary layer divided by the thickness of the boundary layer. So we are seeing in this region, so it will be delta T is the boundary layer thickness, and this should be equal to the heat transfer coefficient times delta T. So this implies H is K by delta T. And from this we can define Nusselt number as H times the local Nusselt number as HL by Hx by K, so which is x by delta T, which can be related as x by delta times delta by delta T, which would scale as x by delta, you already know from this, is Reynolds number to the power half, and delta by delta T is the inverse of this, that is Prandtl to the power 1 by 3. This is our local Nusselt number scales for case 1, which is delta greater than delta T. And when will delta be greater than delta T? As we see here, delta by delta T is proportional to Prandtl number. So if PR is greater than 1, Prandtl number is greater than 1, then delta will be greater than delta T. Now similarly for case 2, this equation remains the same because we are applying at this point, and beyond this point u will be u infinite. So nothing changes in this equation. Delta by x will still be proportional to, like, will still scale as Rx to the power minus half. Now coming for the energy equation. So previously we need to consider the velocity at the end of boundary layer here. But now velocity needs to be considered at the end of thermal boundary layer, which is again the free stream velocity u infinite. So the equation will become u times del t del x. We are scaling between these two terms. So here I have u infinite times delta t by x would be scaling as alpha times delta t by y will be the thermal boundary layer thickness delta t square. So again I can substitute u infinity by x as nu by delta square. That will be nu by delta square would be scaling as alpha by delta t square. So this implies delta by delta T would be scaling as PR to the power half. So again, the same relation for Nusselt number, we can directly substitute here. Nusselt number will scale as x by delta times delta by delta T, which is x by delta is Rex to the power half and delta by delta T is PR to the power half, Prandtl number to the power half. So this is for the case when Prandtl number is less than 1. So for oils and other substances for very high very high viscosity, which have Prandtl number very much greater than 1, that follows this relation. And for like liquid metals or something which have high thermal conductivity, Prandtl number will be less than 1 and they follow a different kind of scaling with Nusselt number. This is also discussed in the lecture videos. I kind of just wanted here because this is something that will be required for the next problem. Are there any questions in this? I guess there are no questions. Okay. So let's say we have a rectangular cooling plate. Let's say this is my length, say 1 meter and 0.2 meter. And I'm trying to cool that plate by blowing in air, which is at U infinity. I can do it in two ways. One configuration is this. The other configuration is I can just rotate it 90 degrees so that now the plate becomes like this, where you have this as 0.2 meter and this as 1 meter and air flows in this way. This is orientation 1 and this is orientation 2. So you are the designer, let's say, and you want to understand which configuration is suited for your particular case, like which will give you better results. So your objective is to cool this particular rectangular plate. This is some kind of a sensor that is getting heated up, some kind of an electronic chip that is getting heated up, and you have a fan near the chip. Now you have to decide how to orient your fan. You can either put fan here or here. So does the orientation matter? First question is, would the orientation matter, or if it matters, which one is better and why? I'll give you a couple of minutes to think and then we'll discuss. Okay. First, let us answer. But first, let us agree on one point. Does the orientation matter, or doesn't it? Like any orientation gives you the same value because the total electronic chip, the area of the total chip is same, whichever way you keep your fan in, and the total amount of heat generated is also going to be the same. So, will orientation matter? It does matter. Does matter. So it does not matter. Okay. So anyone who says otherwise. So how do we like approach these kind of problems? So from what we already understand, we know that from what I told you before, that the shear stress is inversely proportional to delta. This is something that we already agreed on. Let's say U infinity is same everywhere. Now similarly, when we apply the same analysis to thermal boundary layer thickness, your heat transfer QW is going to be proportional to, or will actually scale as, thermal conductivity of the fluid times the temperature difference between the fluid and the free stream. Like if whichever way you orient, the surface temperature is going to be same initially, divided by the thermal boundary layer thickness. So here also it follows the same logic, that the heat transfer from the surface will be inversely proportional to the boundary layer thermal boundary layer thickness. So if I want to increase my heat transfer, my thermal boundary layer thickness has to be reduced. So in case 1, we are having flow in this direction. So this is my 1 meter surface. So my thermal boundary will keep growing, and it will reach something like this. This is for a 1 meter surface. In case 2, the boundary layer is developing over a very shorter length. So it would end somewhere here for, let's say, 0.2 meter. So which means the thermal boundary layer thickness for case 2 is going to be lower than case 1, right? So which means the heat flux is going to be higher in the case of case 2 compared to case 1. If because areas are same, I'm just considering heat flux. Otherwise, I would have to multiply by area to compute the total heat flux. And again, there is one common mistake that I have seen in last year is where people actually use the concept of Nusselt number directly, where they say that Nusselt number is given because both of the same fluid, Prandtl number is constant. So Nusselt number will actually scale as Reynolds number to the power half, which is what we discussed just in the previous slide, where irrespective of whatever greater than or less than 1, it will scale as Rex to the power half. So they start from the analysis that Nusselt number is going to be scale as Reynolds number to the power half. And they know that in one case, the characteristic length is 1 meter. In the other case, the characteristic length is 0.2 meter. So Nu1 by Nu2, case 1 by case 2 would be like proportionality constant is going to be same for both of these configurations. Then you'll have Re1 by Re2 to the power half. Since viscosity and free stream velocity are same in both the cases, so this would eventually come to L1 by L2 to the power half, which is greater than 1 because L1 is 1 meter and L2 is 0.2 meter. This is greater than 1. So they will come to the conclusion that orientation 1 is greater than orientation 2. Is this approach correct? Yeah, I've actually told you that this was a mistake before, so maybe I shouldn't be asking that question. So what is the mistake in this approach? The key thing to remember whenever we deal with Nusselt number is because so not only Nusselt number, any non-dimensional number is we will be having certain characteristic length or some characteristic dimensions in while they are defining that particular number, and those have to be always be kept in mind because here Nu1 is defined as Nu is basically defined as h times characteristic length by k, and this characteristic length is actually different for case 1 and case 2. So just because Nusselt number for case 1 is greater than case 2, we cannot come to the conclusion that this will give a higher heat transfer compared to the second one. That will happen only when both the cases have the same characteristic length, which is not the case in this particular problem. What happens in this particular problem is this will actually come because K kappa is the thermal conductivity of air is same for both of this. We'll have H1 L1 by H2 L2 to be L1 by L2 to the power half. So which essentially comes to H1 by H2 being L1 by L2 to the power minus half. So which is actually less than 1. And this is a heat because both of them have the same surface area. The heat flux will be proportional to H times area, and area is same for both of them. So Q1 by Q2 will be H1 by H2, which in this particular case is less than 1. So which means orientation 1 will actually give you lower heat flux compared to orientation 2. But then as you can, this is like if you are strictly going from the scaling analysis that we discussed, this is how you would approach the problem. Or you can also start, think in a different perspective where you start from this equation that your heat flux is given by K, like would actually scale as K times delta T by the thermal boundary layer thickness, and delta T is assuming both same for both the cases, both the orientations, and thermal conductivity is also same for air in both the cases. So the heat flux will be inversely proportional to delta T, and we already know that as you go away from the leading edge, your boundary layer thickness will keep increasing. So at 1 meter, I'll have much larger, like much thicker boundary layer compared to at 0.2 meter. So which would mean 0.2 meter will give me more heat flux compared to the 1 meter one. Either way, you would reach the same conclusion. And the important point here that keeps coming up when you deal with convective heat transfer is the second aspect with respect to the total drag force and the shear stress. The shear stress, as we discussed before, is inversely related with delta. So which means using 1 meter will give me will reduce the shear stress. But because I reduce the length to 0.2 meter, the shear stress will actually increase now. So both the heat flux and shear stress, both of them will increase as the boundary layer becomes thinner and thinner. So what this means is whenever the shear stress increases, then I have to use more pumping power, which means there is more friction. So I have to use more power to pump the air on the surface on this particular chip, which means I'll be increasing my power consumption for the fan. So how do you decide, like if you are the designer, how do you decide which orientation to use depends on your particular requirement where if in your particular case, increasing the heat transfer is more important and is like gives you much more benefit than the cost incurred for pumping the air over this particular one, then you would be choosing orientation one. If it is the other case, then you would be choosing orientation two, which what usually happens is you will have to compromise between both of them, do some kind of optimization, and then you will come up with a orientation where you kind of get like you kind of compromise that okay, I will not get the 100% this or this, so you'll compromise somewhere in between, depending on whatever your cost benefit trade-off is. Again, that would be some like we can pose this as a mathematical problem and then solve it, which is again something that we will take up little later. But for now, the idea is for you to understand that orientation does impact the heat transfer as well as the drag force. So this is with respect to shear stress. Okay, I need to also comment on the drag force. What happens to the total drag force? Or maybe we'll take it up as a separate problem. You can take this as a self exercise. We are almost like okay, almost 6:30. So take this as a self exercise, like a homework kind of a one, where try to estimate the total drag force, which will anyway take up in the next problem. Yeah. So the same one with different dimensions. So consider the cooling plate. It is operating in a fluid-free stream with the velocity given as 2 meter per second, and the temperature difference between the plate and the ambient is 50 Celsius. To find the full scaling rate, instead of doing the experiment on the actual one, we actually did a 1:3 scale model where the length is given by 0.2 meter and width is given by 0.1. So it is essentially 1:3 scale model using the same fluid so that the properties are constant. During the test, when I'm doing the test, we match the Reynolds number. So both the actual one and the model have the same Reynolds number. In the model, the heat flux is given by 180 watt and the temperature difference is observed to be 40 Celsius. Now you are asked to find the velocity in the lab scale in terms of UP so that the dynamic similarity is matched and you have to calculate its value. Second, using the non-dimensional scaling laws that we already discussed, determine the total heat transfer rate for the prototype without evaluating fluid properties or empirical constants. So as of now, we do not know the actual correlation for Nusselt number, but we still know the scaling analysis. So just using the scaling analysis, if you know the heat transfer in the model, we can actually estimate the heat transfer that is going to happen in the prototype also. So this is again something that you would have already done in your fluid mechanics. This is just kind of refreshing, like the first 2 weeks are kind of refreshers. Even next week is going to be like for half of it, it's going to be on the just the momentum equation of boundary layer, and then we will start the energy equation. Maybe I'll give you 5 minutes to solve this. And maybe one more point I would like to highlight here is why did I directly say that NUP and NUM are equal? So when we do dynamic similarity, we'll have to like how did I come to this conclusion that NUP and NUM are equal? Sorry, can you just repeat again? Yes. So that is actually written, yeah, because we want both the model and prototype to be same. We have matched the Reynolds number. So because Reynolds number is matched, and we know that Nusselt number is only a function of Reynolds number because it is also given that it is the same fluid. We know that Nusselt number scales as RE to the power half because same fluid Prandtl number effect is not there. So it is only the Reynolds number that affects this particular configuration. And because Reynolds number is matched, Nusselt number is also going to match. But in some scenarios, you might not be actually matching the Reynolds number. Then this particular relation will not hold. But the scaling relation still holds. So if the Reynolds numbers are not matched, then you can still use the relation that NUP by NUM equals, if they are the same fluid, then it will have this relation. But you have to be careful whenever you use this kind of relations because this implicitly assumes some things. Like for example, we are saying Nusselt number scales as Reynolds number to the power half. This is valid only for laminar boundary layer profile. So you need to know what the Reynolds number range is for which this particular relation holds. So for case of flat plate, Reynolds number has to be less than 5 to 10 power 6. For duct flow, it will be, we will discuss that later also. But I just want to highlight here that whenever you use some kind of relations like this, you need to make sure their region of applicability, and then from there you do the scaling thing. Okay, now this is straightforward problem, I think. So Nusselt number is given by this relation because both are matched. NUP will be equal to NUM. So this is HP times LP is HM times LM. Because fluid is same, I've removed the thermal conductivity on both the sides. The heat transfer rate, if I have to write, that will be HP, sorry, heat transfer coefficient times the area times delta T by HP. So we know HPLP equals to HMLM. So these things will go off. So we'll have WM by WP times delta TM by delta T. Delta TM is given as 40, delta TP is 50 Celsius, and WM by WP and WM are already given. Again, I've kind of implicitly assumed one thing here, which you might actually do in some different way. When I've defined the Nusselt number, I have actually used LP and LM. It could also be the other way around, HP times WP times HM times W. Like just as we discussed, depending on the how your free stream is flowing relative to the plate, it can either be L or W. But usually the convention is, if nothing is specified in the problem, L is usually taken as the direction in which the flow is happening. That is the kind of a convention. So now we'll just stick to the convention, and this is kind of a straightforward arithmetic. You can substitute the values, and QM is given, so QP you can calculate. I'm getting this value to be around 675 watts. You can calculate and check again, but I think the basic idea is clear. This is with respect to the heat transfer, and one part that we have not touched up until now is the drag force. So which is again something that I wanted to discuss. So let's say you have an underwater plate of length so and so and with 0.5 meter, which is operating in water at a free stream velocity of 1 meter per second. To determine the total skin friction drag force, you made a model which is of 1 is to 5 scale in water flume using same water. So both are under similar fluid, and you have matched the condition that the Reynolds number in your actual case as well as your test case are the same. During the experiment, the force sensor on the model is the one that you made, is 3.2 Newton. Calculate the required and calculate the total drag force on the prototype. So in the previous problem, we know what is the heat transfer rate on the model, and from there we calculated the heat transfer rate on the prototype. So now what we would do is for the drag force. The first one is again straightforward. So the Reynolds number is matched. So you have because same fluid, I'm removing the viscosity term. So UPLP by nu. LP is given and it is a 1:5 model. So LM is given. So from this you can calculate UM. This is a straightforward one. So how would I calculate the total drag force? So you have a surface, the total drag force exerted on the surface because of the fluid that is flowing is given by the shear stress times the total surface area of the plate. And shear stress is related with the skin friction coefficient, which is also defined in these videos as basically you have half times rho U infinity square. This is the dynamic pressure times the skin friction coefficient. And CF will actually scale as, what is the scaling of skin friction coefficient? We discussed this little while ago that your skin friction decreases as you go along the x direction. And then, like, how would it be? Or I would write it directly in terms of Reynolds number, so it will be clear. Your local Nusselt number will scale as Reynolds number to the power half, while the skin friction coefficient will actually scale inversely proportional to Reynolds number. As you go farther away from from the leading edge, your skin friction reduces. So the total drag force will be something of this kind. Half times area. Now, because we know that the Reynolds number is matched between model and prototype, this particular effect can be gone, and then we have on the model as well as on the prototype given by square times LMWM by UP square times LPWP, which will give me you can actually see that this term actually goes to 1. It's like the total drag force on both the model as well as your prototype will be the same. So which means on prototype also it will be 3.2 Newton. So what is the key point that I want to highlight here? Again, another point is whenever the scaling happens, what do we mean by 1:5 scale model? What are the dimensions that we are reducing? So the physical things, I mean, the things that you might already see here is I have a plate like this, is an actual plate. Then when I scale it down, it becomes something smaller like this. These are the only two dimensions that we are considering as far as these problems are concerned. But in reality, what happens is this surface, whatever you're having, is not so smooth. It will always have some kind of roughness. So when we are kind of doing this geometric scaling, if we expect these relations to hold perfectly, then ideally we should also be scaling this whatever roughness that we are having here. So if I have this roughness, let's say is given by Ks, some kind of a smoothing value, the Ks value here divided by the boundary layer thickness that I'm going to get in the actual case should also match with the values here. Because I have scaled down, delta will also reduce, which means I have to use I have to, when I made a model, the model also needs to have even smoother surface than the actual one, which may not always be possible. So this is another challenge that you will encounter when you actually do experiments, is when these scales do not exactly match, you cannot infinitely make it smaller. There will be a certain like point beyond which you cannot make it. Like I can always make it even smaller and smaller. You can think like that, but we cannot actually go smaller and smaller. There exists a point when this becomes important, when the surface roughness becomes important, and you cannot actually scale them. So for certain regions, even though these two do not actually match perfectly with each other, the disturbances that are caused because of these small variations will not actually grow or will not actually cause any kind of deviations in our gross properties like the drag force or in case of heat transfer. But beyond a point where this number becomes significantly important, when the surface roughness becomes comparable to the boundary layer thickness, they actually affect the flow, and then your drag force or heat transfer will actually change. This is another thing that is important when actually we move to turbulent flows. Again, as I said, this we will discuss once we move to turbulent flows. This is just a kind of an anchor point here so that you can connect with it later. The point here that a kind of a takeaway is to understand that you cannot infinitely make it smaller. There exists a limit, and that is essentially because you cannot make it smoother and smoother and smoother. And there are other challenges also. The one challenge is the drag force is same on both the actual surface as well as the small surface. Because drag force is the same, the shear stress will actually increase. So the shear stress is given by drag force by the total surface area. So if I were to compare the model to the prototype, so both of them have the same drag force, which means this will be AP by AM. So in this particular case, on a 1:5 scale, the model will experience actually 25 times more shear stress compared to the prototype. So which means if you are using some kind of nuts or bolts to anchor this particular plate to something, then you will have to design them accordingly. The one that are used in the actual prototype will actually have a different capacity, like will actually experience stresses different from the bolts that you are going to use on the smaller one, because the same amount of force is being exerted on both of them. So these are all other things that you have to consider when you are kind of designing experiments with, like when you are trying to do your own experiments. But the idea is clear, I guess. Like scaling analysis, like we do not even have to know the actual correlation between these two values, as long as we know that as long as we know the scaling analysis, we can do this kind of stuff where we have a prototype and a model. We can always do the experiment and then find what is going to happen in the real prototype. I have this one last problem. This also you can take it as a take home exercise. I'll upload all these slides on the Google Drive link. So this is just as I said before, the drag force is going to be the same. So you calculate the shear stress and understand that because it increases, your bolts or whatever pins that you are using to mount your particular plate will actually be designed accordingly. So this is the maximum allowable shear stress. So you will have to use larger pins so that they will take so that you remain within this acceptable value of tau. I think this is. Are there any questions in this? So the idea is again same as follows. You calculate tau w by tau m, which will actually be proportional to, which will actually scale as. So this will be same as before, 25. But because you have 4 pins, so you have to calculate the load 3.2 Newton divided by the corresponding area. From this you calculate the area and then you'll get the shear stress. So from the prototype case, you'll extend it to the model case and then see whether the value of tau is less than 2.5 megapascal or not. If it is, then you are fine. If it is not, then you have to increase your area accordingly for that particular pin. Are there any questions? No questions. Okay. Yeah, then these are the ones that I have for this week. To summarize what we have discussed, we started with a recap problem of Newton's cooling law. And then we discuss the Reynolds transport theorem, where we relate the properties of system with control volume. And subsequently, we discuss the importance of viscous dissipation term in energy equation. And we found that it is actually negligible for low speed flows. And then we moved on to boundary layer equations, basically the scaling arguments, where we have differential equation with multiple terms. Then we actually compare the order of magnitude analysis, and then we pick regions where some magnitudes, some terms are important than the other terms. And from there, we discuss for fin case, where we observe the regions where conduction is dominant, where internal heat generation is dominant, or convection is dominant. And we understood how to do the balancing from one term to other term in case of boundary layer also, and from which we obtained two difference of scaling for Nusselt number depending on Prandtl number greater than 1 or less than 1. We got two different scaling relation for Nusselt number, and then we discussed some problems to understand to kind of so you can relate with what we had discussed in the course with some of the practical applications. Yeah, these are the things I have for this week. Yeah, please do fill in the feedback form. So if you have anything, you can put in the feedback form. So I include them for the next week. If you have any other questions, we can discuss them. Otherwise, you are feel free to leave the session. Okay, thank you for joining, and we'll meet again the same time next Saturday from 5 to 7. Yeah, thank you.